Hi everyone, I'm Liron Faybish, and first I want to thank you for inviting me to talk here in Women in Data Science Vancouver. It's an honor to be a part of that community and leverage the issue of women in data science positions. Today I'm going to talk about the topic of keeping sensitive data safe using recommendation systems. First, few words about myself. I'm a data scientist on PayPal for more than 5 years. I am part of the cybersecurity threat oversight team, which is part of the information security organization. We are a team of security researchers where each one has a different perspective and unique point of view in order to cover as many security issues as possible. My role is finding machine learning solutions for information security problems. And as part of my job, I'm mainly focusing on insider fraud detections and about keeping our data safe and secure. In addition, I have MSc in Information System and Software Engineering from Vancouver University. Today, we are going to talk about protecting our data in the organization. Many organizations are using a massive amount of data for their day-to-day job. And usually, most of the organizations are using databases to store the data, and users are performing queries in order to access, extract, or update the data. Sometimes this data might be sensitive and shouldn't be exposed to all users. For example, data like passwords, phone numbers, addresses, and accounts is very sensitive and should not be exfiltrated out of the organization. Keeping this data safe and secure is one of the main issues that most of the organizations need to deal with, because it can cause a real damage to the company if this data is leaking out to the wrong hands. So the problem we are trying to solve is the need to improve the control we have in the organization on our sensitive data. It means that we need to find a way for keeping this data safe and prevent potential security incidents and any possible misusage of this data. It means that we need to make sure that only authorized users will access it and detect any different behaviors in the user's data access patterns. In this talk, I'll show you how can we use recommendation systems for the problem of anomaly detection and how it can help us detecting unauthorized access to our databases. We will talk about recommendation systems in general, and specifically about implicit feedback and its implementation in Python. Afterward, we will talk about how can we use recommendation systems for anomaly detection for databases access, and I'll show you the experiments I made and how it's proving the accuracy of the method. So let's start with recommendation systems. So what are recommendation systems? In recommendation systems, usually we have several items, and the goal is to predict the rating a user would give to each item and suggest relevant items for him. For example, if the items are movies, like in Netflix, we're trying to predict movies you would like based on previous movies you've already watched and recommend it to you. There are several methods for finding those recommendations. The most popular method called collaborative filtering, which based on the assumption that people who agreed in the past will tend to agree in the future. Collaborative filtering is using similarity scores between users and items in order to provide recommendations. If we want to recommend an item to a user, we can look for other users who share the same rating patterns with our user, which means that they have the same preferences. We are using the ratings of those similar users in order to calculate the predicted rating of the items and recommend those items to our user. For example, if we have 2 users who usually eat pizza and salad every day, and one user is buying Diet Coke one day, so it will be probably a good option to recommend the other user to buy Diet Coke as well. There are 2 types of feedback when talking about recommendation system. One is explicit feedback, where we have a direct input from the users regarding their preferences. This way, we know exactly how much a user like or dislike a particular item by providing a numerical rating to it. For example, a user is rating a movie between 1 to 5 stars, or rating a dish in a restaurant from 1 to 10 according to how much he likes it. But users probably don't want to spend time rating the items they're using. So usually this type of feedback is hard to get. Another type of feedback, which is more popular, is implicit feedback, where all we have is only the users and the items interaction. It is data we gather from the user's behavior with no ratings or specific actions needed from the user. For example, if a user has watched a movie 5 times, the system infers that the user is interested in it. More examples of implicit feedback are items the user purchased, how many times they played a song or watched a movie, how long they've spent reading a specific article, how many times they clicked on a website link, and so on. The upside of implicit feedback is that we have a lot more data, but the downside is that it's way more noisy and we can't always understand its meaning. For example, with stars rating, we know that 1 star means that the user didn't like that item, and 5 stars means that they really loved it. But when watching a movie, it might be that the user watched it and hated it, or loved it, or somewhere in between. And if he didn't watch the movie at all, it might be since he don't like it, or that he would love it if he just knew about it. Later in this talk, I'll explain how can we overcome this problem. Here in our domain, the type of the data we are dealing with is implicit data. There are a lot of methods. There are a lot of methods for calculating those ratings. One of them is called matrix factorization. In this method, the past ratings are stored in a sparse user item matrix, where each cell stands for the rating a user is giving to an item. This matrix is sparse because each user has only few related items, and usually there are no users who rated all items. The matrix factorization method suggests using low-dimensional representation of users and items in a shared latent factor space. And by using those user item latent space, we can infer unobserved preferences. The idea is basically to take the large user item matrix and factor it into some smaller representation of the original data. By using matrix factorization, we are able to discover latent features for both items and users, and use it to calculate the prediction of a rating with respect to the similarity in the user's preferences and interactions. The multiplication of the user and item matrices gives us the predicted rating matrix. For example, in order to calculate the predicted rating a user U will give to an item I, we need to calculate the multiplication of row U in the user's matrix with column I in the items matrix, which is the UI cell in the predicted rating matrix. Using this reduction method helps us also reducing the complication of the rating calculation, and also give us better results because now we have some sort of features for each user and each item. So we can express each user as a vector of their taste values, and each item as a vector of what tastes they represent. This factorization method gives us also the ability to find connections between users who have no specific items in common, but share a common taste. The goal is that the predicted rating matrix will reflect the true preferences of the users. Common loss function for user U and item I can be expressed as the following. We are trying to minimize the squared error of the difference between the real rating and the predicted rating, which is the dot product of the user and the item vectors. In addition, there is also the regularization term in order to prevent overfitting. Minimizing this formula using the regular optimization methods works better for explicit feedback, but doesn't work well when dealing with implicit feedback data. The main difference between implicit and explicit feedback is how we are dealing with missing values. In explicit data, it's just unknown data. But for implicit feedback, we cannot assume that, since there are some information in these unknown values. So we need to find a way to learn from the missing data. In the next few slides, I'll show you a way for adjusting the matrix factorization method for implicit data. The approach we are going to use here with our implicit dataset is based on the method that mentioned in the paper, collaborative filtering for implicit feedback datasets. In the method mentioned in the paper, they used a binary preference. Has the user observed the item or not? And they mapped that preference with the weight of confidence we have for that score, which is the strength of the preference. Missing values are negative preference with a low confidence, and existing values are a positive preference but with a high confidence value. In the paper, they used RUI for representing the observation for user actions. For example, in the movies domain, RUI could be the amount of times user U watched movie I. The next formula is PUI, which is the preference of user U to item I, and is equal to 1 if RUI is greater than 0, which means that the user consumed the item I. Or it will be equal to 0 if the user didn't interact with the item at all. Later, we are calculating the confidence. CUI is equal to 1 plus alpha multiplied by RUI. The confidence is higher when the user interacts more with the item and uses it more often. The rate that the confidence increases is set using a linear scaling factor alpha. They also added 1 in order to have a minimal confidence even if R is equal to 0, And as can be seen in the formula, when we have only one interaction between a user and an item, the confidence will be higher than the confidence of an unknown data because of the alpha value. Now we are trying to minimize the following loss function, which is the confidence multiplied by the square difference between the preference and the dot product of the user and item vectors. And again, adding the regularization term. This cost function depends on M and N, where M is the number of users and N is the number of items. And even for typical datasets, M multiplies N can easily reach a few billion. And the regular optimization methods, such as stochastic gradient descent, SGD, wouldn't work well for this type of data. Therefore, in the paper, they offer to use alternative optimization method, which is the alternate least squared algorithm, ALS. This method suggests fixing each factor at a time. If we are fixing the user factors or the item factors, we can calculate the global minimum. It means that we are alternating between recomputing the user factors and the item factors. And when fixing either the user or the item factors, the cost functions become quadratic, so its global minimum can be easily computed. And each step is guaranteed to lower the value of the cost function. Due to time limitation, I won't dive deeper into the deep mathematical calculation. If you want to know more about it and understand the full process of the algorithm, you can read it in the paper. After solving everything and calculating the matrices, we can finally move to the recommendation process. In Python, there is an implementation of this algorithm in the implicit library. This library provides fast Python implementation of several different popular recommendation algorithms for implicit feedback datasets. And one of them is the alternating least squares algorithm as described in the paper. In order to install it, you just need to do pip install implicit and you will be able to import it and use it. For using the ALS algorithm, you need to initialize the model first using implicit.als.alternate least squares, and then choose the number of factors, which is the number of latent features to compute, then choose the regularization factor to use, and also choose the number of ALS iterations to use when fitting the data. Of course, there are a few more parameters in this function that you can find in the documentation, like use GPU or whether or not showing the loss log, but the parameters I showed you are the main parameters you need to set. Later, we need to create the confidence matrix. So we are choosing the alpha value, which here is 40, and multiply it by the sparse user item matrix. Then we are fitting the data to the model using this confidence matrix and creating our model. Now that we have the trained model, we can move to calculating the recommendations. We can recommend items for the user using the recommend function. We are choosing the user we want to recommend items to, and also we are choosing the number of items to recommend. The functions also need the original user item matrix in order to filter out the already used items. The function calculates the top n recommended items for the user and returns a list of items IDs and a corresponding score for each item. For example, item number 566 received a score of 0.86, which is higher than the score item 166 received, which is 0.7. We can also calculate the top similar users and the top similar items using the following functions. Those functions have the same structure. For example, with the similar items function, all you need to do is just set the ID of the item and also set the number of top close items to calculate, and you will get a list of top similar items along with their corresponding score. Same with the similar users function. One last interesting function is the rank items function, where you can choose a user and a set of items you want to rank, and the model will calculate their score and rank the items according to the preference of the user. Again, the function returns the IDs of the items along with their corresponding score. As you can see, the scores aren't always between 0 and 1. It happens because there is no explicit scale here. The scores are used only for sorting and ranking the recommendations, where the higher score means the most recommended item. When calculating the dot product of the users and the item vectors, we are trying to make it as close as possible to the real preferences. But since there are no boundaries, it can take any possible value. By finding the optimal parameters, we push those values close to 0 and 1. But when adding the confidence weight and the regularization, those additional factors may push them in different directions. So we don't always end up with 0 to 1 value. Okay, now back to our problem. Our domain is datasets access, and the actions we observe are users who access to tables and extract or update the data in it. So our objects are users and tables. And the relationship is that the users are consuming the tables. So the tables are the items. Users are accessing the table using queries. So we are looking on the amount of queries each user performed on each table, and that would be our implicit feedback. In general, high amount of queries on a table means that the user likes the table. It's relevant for him. But if there is a low amount of queries on a table, it means that the user disliked the table, or as we discussed a few minutes ago, it may be because he needed it only for a few times. In addition, if the user didn't access a table at all, it could be because the table is irrelevant to him, or because he didn't know about it, or didn't have the chance to use it yet. Again, that's exactly why in the algorithm we are using, they use the confidence value on the user's preference. And in the cases where we don't have many interactions with the table, the confidence will be low. The problem we are trying to solve here is finding anomalies in those actions of access to tables in the database. Basically, it is events of unexpected or unauthorized tables access. For example, if someone is working on a project of type X, he is usually accessing tables that related to this project X because that's what he needs to perform his job. But what if suddenly he's accessing all the tables, which doesn't relate to his project and doesn't relate to any one of his team members' projects and might contain sensitive data that he doesn't supposed to have access to at all? For example, we don't want someone from the user interface team in Netflix will access the customer's data. This type of data is not relevant for user interface, and there is no excuse for this user to access this data. So we need to prevent those events and keep our data safe. We should create an alert for those kind of actions. So we'll be able to protect this data and make sure it doesn't exfiltrate it out of the organization. But how recommendation systems are related to all of it and how it can solve our problem. As we mentioned above, our goal is detecting anomalies in the user's usage patterns. Detect when the user is behaving differently from the way he's supposed to behave and performing actions that doesn't fit with his previous actions. Usually in recommendation systems, we are looking for items that the user is supposed to like and recommend it to him. But here, in this case, we are looking for the outliers, which is the opposite direction of recommendations, the items that the user is unlikely to use. For example, in the movies domain, instead of focusing on movies the user would like, we are looking for the least expected movies with the lowest probability that the user would watch. So in our solution, we are looking for those unrecommended items that the user is not supposed to use and alert when he's using those items that might cause dangerous consequences to the organization. So we need to build a recommendation model based on the database's access logs. We need to count the amount of queries each user performed on each table, and this will be our implicit data, which is the sparse user item metrics. We are building the ALS implicit model using the Python library on the database's access data. We need to set the values for the regularization factor, the number of ALS iterations, the number of latent factor to use, and the value of alpha, which is the scaling factor of the confidence. After setting all of those variables, we can fit the table's access data to the model, calculate the score of each new access to a table, and see if the score is high or low and alert accordingly. We decided to train the model using 6 months of queries data, so we'll have enough data for training the model. We also decided to count new access to a table only if the user is accessing the table using different queries on the same day. It means that if the user is using the same query for several times in the same day, we will count it only once. But in the next day, it will be counted again as a new query. We did that because we wanted to remove automated queries that runs the same query over and over again and creates really high amount of accesses to tables. It creates a lot of noise in the data. And we wanted to reduce that noise and make the model as close as possible to the real access patterns. In addition, we also set a threshold for minimum access for users and tables. And we filtered out rare users who accessed only few tables, and also tables that almost no users has access to. So now we have a trained model that can calculate recommendations. But how can we know that it's actually working? In order to prove the accuracy of the model, we performed 2 experiments where we tested the output of the model. In the first experiment, we simulated multiple accesses to tables and checked the score the model gave to each access. We created a test set of 500 events of users who access to tables. We didn't use those events for training the model, and it was only used for the test set. We decided to consider for the test set only events of users who access to a table for more than 10 times. So we'll be able to be sure that this table is indeed relevant for the user. We chose those events because we are dealing with implicit data. And if we are choosing a user who accesses to a table only once, it could be that he accesses it by mistake and it's irrelevant to him. And we wanted to be sure that we are testing only known preferences. So we trained the model using the access data, and then we calculated the scores for the test set and plotted the results on the following histogram. As can be seen in the histogram, almost all of the observations received high score, around 1, which indicates the accuracy of the model, since it means that the model is predicting the scores correctly according to the real preference of the user. Because we chose for the test set only items that we know for sure that the user actually liked because he used it for more than 10 times. The second experiment we made is based on the assumption that in the world of databases access, similar users who works on the same team or works on the same type of projects will access the same groups of tables that related to their projects or to their team. And the outliers are when someone is accessing a table that he didn't access before, and it doesn't relate to any other of his previous tables or to any of the tables of his similar users group. So in order to simulate good and bad access to tables, we are choosing 500 random users, and for each user, we are choosing 2 unseen tables that this user never accessed before. The first table is taken from the group of tables that his team already accessed and used. And the second table is taken from the group of tables that no one from his team accessed before. Now we are feeding those scenarios into the model, and we are calculating the scores, which is the rating of the items that the model calculated for each simulated use case. In order to evaluate the results, we calculated the kernel density estimation of the scores. As can be seen in the graph, the blue tables, which are the tables taken from the same team, received higher scores than the red tables that was taken from other users. You can see the separation between the scores of the blue and the red tables, and how the outliers we simulated received a lower score than the blue relevant tables. In addition, you can see that most of the scores in the red group are around 0, and most of the scores in the blue group are around 1. It means that the model indeed was able to identify the suspicious access to the unexpected tables and separate those scores from the good data. In addition, we also calculated the ROC, which is a popular evaluation metric for binary classification problems. And the higher the area under the curve is, the AUC, the better the performance of the model at distinguishing between the positive and negative classes. So we calculated the AUC, and it was around 90, which is another indicator that our ALS model is working the way we wanted it to work. I also wanted to share that after creating this project, testing the model and evaluating it, me and my colleagues in PayPal decided to file this idea as a patent in the US Patent Office. And now you can find it and read all about it in Google Patents. For conclusions, I presented the idea of using recommendation systems for the problem of anomaly detection. We talked about the idea of recommendation systems in general, and specifically the ALS algorithm for implicit data. Later, we discussed about how we can use this algorithm for the database's access problem, and about using the opposite direction of the recommendation process in order to find anomalies instead of recommendations. Now we can detect unauthorized access to tables, get a score for each new access, and alert accordingly. In order to decide if a score is an anomaly or not, we need to set a threshold. Based on the scores the model calculated, we can define the threshold for suspicious access and alert or block each unauthorized access that received a score below this threshold. In addition, we can identify the set of sensitive data and give it a smaller threshold so we'll be able to control the sensitivity of each access, and tables that contains more sensitive data will get more focus, while tables with regular data will get a higher threshold. This way we can play with the threshold in order to control the noisiness of the alerts according to the sensitivity of the data. Possible challenges in that method could be how the model is treating new users. In recommendation systems, this problem is known as the cold start problem, which is the problem that the system cannot draw any inferences for users or items that it has not yet gathered sufficient information. In our domain, One solution could be looking at the clusters of the user's team. And another solution could be looking at who this user met the most, and that will be his close user cluster. And we can calculate the average of that cluster, and that would be his initial vector. And when we will have enough data, we can update this vector according to his real preferences. Another challenge could be changes inside the organization. Employees who are moving from one team to another, changes of responsibilities, and so on. This could confuse the model, since now there are users who access to tables that are far from the previous tables they used to access. We can solve this problem by defining some grace time when we are learning the new vectors again, and canceling the alerts from that team for a while until we will get the new updated vector. Possible future steps on this area could be using this mechanism for the granting access process in the organization. For example, if a user is requesting for a specific access to a table, we can calculate the score of that access. And if the score is low, which means that the probability that this table is relevant for that user is low, maybe we should ask his manager before granting that access to him. One more thing could be learning and getting insights from the scores and leverage teams collaborations. For example, creating the teams clusters according to their preferences vectors, and suggest those teams, which is in the same cluster, to collaborate and learn from each other since they are working on the same type of data. We also can combine the scores with other fraud detection alerts in order to get more accurate results and reduce the noisiness of the alerts. Thank you for listening to my talk. If you have any questions, please feel free to reach out to me. Thank you.
Thank you so much for the talk. And I see there are 4 questions submitted in the Mentimeter. So let's go through them. The first 2 have 2 votes, so we can start with those. So first question is, are you able to share an example of a security attack detected by your model?
Unfortunately, no, because of the sensitivity of the area, PayPal doesn't really share those events. So that's the experiments I shared with you are the only experiments I can show. Sorry.
Any follow-up from the audience for your question, or you're satisfied with the answer? Okay. Second question, what are the practical applications of leaving out the tables that had a low or no number of people accessing?
We are keeping out the tables that have low numbers of access because we are not learning much from this data, and it's just noise. So at the beginning, like it's common to remove those tables because it doesn't contribute much to the model, and it's just noise.
Okay.
It added just sparse vectors.
Okay, makes sense. Third question, how do you decide on the size of training data in terms of number of user, table, and time coverage?
I think if I'm understanding correctly the question, you're asking why I decided to train the data using 6 months of data. I did some experiments in order to see how the right amount of data I need in order to get an accurate model. At the beginning, I tried like with 1 month, and then I tried with 3 or 4 and 5, and I saw that 6 months is enough data in order to train the model, because we are removing users that has only 1 or 2 accesses, and the same with tables that have a few accesses. So after a few experiments, we saw that 6 months is enough data for the model.
Just curious, have you tried longer?
I tried also 7, 8, and 9 months, and I saw there is no difference in the accuracy of the model. Like there is some improvement from 1 month to 2 months, and like 6 is the top, and there is no more difference when adding more data, because in PayPal we have a lot of tables. So I'm sorry for my husband is trying to sleep the baby to put him to bed. So I'm sorry for the noise. So I saw that after 6 months, the accuracy of the model is the same.
Okay, sounds good. Next question. In the context of a company, how is a recommendation system better than restraining access to the database by having security level associated by the type of positions?
Sometimes I can tell you it happens sometimes that users have accesses to tables by mistake. There is someone asking for access to tables, and somehow they're getting that access that they're not supposed to have. So even if we are looking on the accesses per positions, it's not enough. That's why I thought about this project, because we had that problem of someone. We thought about the problem that someone could access a table that he has for no good reason access to, or I don't know, somehow we gave him this access and we forgot to remove it or something like that. And we wanted to make sure that this user can't actually extract data from the table that it doesn't supposed to use. But it usually happens in big organizations. The amount of the things you can do or you can know, like these things happens. Like in big organizations, these things happen. So that's why we needed another indicator.
Okay. There's 2 more questions just submitted in the Q&A session link. One is, can you talk a bit more about your approach, about how you approach the cold start problem?
The cold start problem, okay. As you know, the cold start problem is when we have new users. So if we have a new user, we thought about 2 options. One, we can look at this team, take an average of the team's vectors, and that will be his initial vector. And another, because at the beginning, like a new employee is meeting a lot of people that somehow we can learn from, and maybe he wants to do some stuff in order to learn the organization, learn the structure of the organization. So maybe we can look at his emails and his calendar and see who he met the most. And those people he met the most, that will be his cluster, and we can calculate the average of that cluster, and that will be his initial vector.
Okay. And last question. Has your model ever flagged you as a potential security threat based on your activity?
What? I'm sorry, it was just noise. I didn't understand what you said. Can you repeat?
Yeah. Has your model ever flagged you as a potential security threat?
I can't share that. I'm sorry. I'm part of the information security organization. I can't share that information.
That's all right. That's all right. I think that's all the question we have for you. Is there any other question from the audience that would like to get answered? If not, then I'd like to thank you so much, Liron, for joining us at Women in Data Science Conference 2020 this year, and for your wonderful talk. And also thank you
for hosting me.
It's our pleasure, and thank you for everyone coming to our session today. I'm gonna stop recording right now, and if there's any more casual questions or networking questions, we can proceed to that. How do I stop recording?
In the bottom, there's a pause stop recording. And there's 1 more question, 2 more questions actually pop out in the meeting.
Okay. Okay, let's go through that first. How does your recommendation system work with GDPR?
GDPR, what is GDPR?
It's a data privacy standard. So it stands, I think it stands for General Data Protection Regulation. It's a EU data privacy standard, I think.
Okay, so I don't know what is it, so I have no idea how to answer this question.
Okay, and then there's one more question. Oh, I think that's the same question twice. So that's the only question. Okay.
By the way, if you have any more questions, I put my email in the end of the presentation, so you can email me your questions.